Thank you very much, guys. I really appreciate you all coming out. Very excited to talk to you all about autonomous path planning for Cislunar trajectory design. As Danny said, I'm Fabio. I'm here with Dr. Brian McCarthy. Go ahead and turn off my camera here and get us going. So before we talk much about the details of the autonomous path planning algorithm, we need to understand what motivates this path planning problem in cislunar space. So what is so challenging about path planning in the cislunar environment? So here we have an image of two trajectories in cislunar space. They're very similar with a very slight perturbation between the two at their initial state. And we see how as time progresses and we propagate these trajectories forward, they diverge substantially from one another. And that just speaks to how sensitive and chaotic the dynamics are in the cislunar regime. And that motivates our discussion for developing path planning tools in this environment. So there's a growing civil and defense infrastructure in cislunar space despite these sensitive dynamics. And because of that, we're going to need effective methods to rapidly plan trajectories in this regime. Cislunar dynamics, as we've mentioned, are highly sensitive, and that makes the traditional path planning methods that we can use in near-Earth space much less effective when we attempt to transition them over to the cislunar regime. Now, trajectory optimization methods require what's called a good initial guess. We're going to dive more into what that means in a second, but just for now, know that the initial guess problem is especially critical given these extremely sensitive dynamics in this environment. So this analysis is going to focus on finding high-quality initial guesses. And what that is a lower fidelity trajectory solution that we can then transition to a higher fidelity model. Obtaining a desired solution from one of these trajectory optimization methods hinges on how good that initial guess is. But finding a good initial guess can be very challenging, and that's because analytical solutions to the 3 and 4 body problems don't exist, and the traditional methods that do exist can be very time intensive, and they require a high level of trajectory design expertise. So that brings us to the central question of this analysis, and that's how can we reduce the need for subject matter expert level expertise when developing these cislunar trajectories? And that brings us to the autonomous path planning tool that we've developed. So this will allow an orbit analyst to very quickly generate several high-quality initial guess options for transfers between orbits in the cislunar regime. But the key here is that it requires only very minimal user input. So ideally, anyone would be able to use this tool, not just individuals with a very high level of astrodynamics trajectory design expertise. This tool leverages some of the known 3-body cislunar orbits and manifold trajectories to inform the path planning process. So what a manifold trajectory is essentially just a known way to leave a cislunar orbit or arrive to a cislunar orbit at a very low cost. So what we can see here on the screen are 6 potential options that this path planning tool might output. So we can imagine how an analyst might very quickly generate a large array of options. In this case, we have 6 different possible options. And then a decision maker could look at all these options and decide which of these trajectories best fits the needs of their mission and do so very, very quickly and with minimal user input. So the dynamical model in which the trajectories in this analysis are going to be modeled are the Earth-Moon circularly restricted 3-body problem. This is going to assume that the Earth and Moon are in circular orbits about the center of mass of the system, and it's formulated in the Earth-Moon rotating frame, meaning that only the spacecraft is going to be moving in this reference frame. So we picked this model because trajectory characteristics are generally retained when transitioned to a higher fidelity model, and it's a nice simple model that we can use for this initial guess analysis. So at a high level, a cislunar trajectory can be constructed by combining together segments from a catalog of known trajectory paths from this circularly restricted 3-body problem. We obtained this catalog of trajectories from an open source library of spatial cislunar periodic orbits that was developed by researchers at UT Austin, and we then augmented this library with both stable and unstable manifold trajectories coming from those periodic orbits in that catalog. So this catalog makes up what we can call the motion primitive set, where a motion primitive is a sort of building block that we can combine together with others of these building blocks to describe all of the sorts of fundamental types of motion that are possible in cislunar space. So this motion primitive approach was developed by Smith, Michelli, and Bozanak out of CU Boulder, and this work attempts to build upon that analysis. So that team of researchers established the viability of using motion primitives in cislunar trajectory design, and they created the concept of building and searching a motion primitive graph to recover an end-to-end trajectory in high thrust applications. And we'll explain what all of that means shortly. And so we've built upon that and demonstrated how this approach also works in the low thrust case. And we've also improved a major clustering step of the algorithm with automatic selection for the number of clusters, dimensionality reduction techniques, and a convolutional neural network approach. And we'll discuss these improvements in greater detail later in the presentation. So here are those works that this analysis builds upon for those of you who are curious and who want to learn more. So we're going to walk through the entirety of the algorithm using a simple example here, and that's how can we find a propellant-efficient path from an L1 orbit to an L2 orbit using these trajectory building blocks. So we see here we're starting at an L1 orbit. This particular example is an L1 Lyapunov orbit. We're departing from there. We want to figure out how can we get to an L2 Lyapunov orbit in this particular example. So the algorithm is going to start by selecting groups of trajectories that are relevant to the design problem. From there, we're going to cluster together trajectories that have similar properties. Next, we'll search for low-cost sequences of trajectories. And finally, we'll both refine those sequences into continuous trajectories and we'll cluster together solutions that have similar properties. So we're going to dive into each one of these steps individually. So first off, selecting those trajectory groups. In this step, we're going to build a high-level itinerary graph that connects together relevant trajectory groups. So what I mean by that is in this case, we know we want to start from an L1 Lyapunov periodic orbit. We're telling the algorithm we know we want to go from that L1 orbit to an L1 Lyapunov manifold trajectory. From there, we know we want to go to an L2 Lyapunov manifold trajectory. And finally, we want to finish off at the destination orbit, the L2 Lyapunov periodic orbit. So this is the high-level itinerary graph that we can use to tell the algorithm how we want to get from point A to point B. So note here that we're starting in this case from a single L1 Lyapunov periodic orbit, going from there to one of many of these manifolds, and again, one of many of the L2 manifolds, and finally to one single destination orbit. We also have the ability to tell the algorithm we want to start not from a single orbit, but from a collection. So we're allowed to start at any of these departing orbits, or we're allowed to end at any of these destination orbits. So we have some flexibility there in the design. So once we've selected the groups of relevant trajectories, we're then going to cluster together trajectories that have similar properties. So in this case, we're going to condense the trajectories together, into clusters of trajectories that are similar to one another. We're going to do this by mapping each one of these trajectories to a vector, a very high-dimensional vector that represents some of the astrodynamic properties of that trajectory. We're doing this by discretizing that trajectory into a number of states along that trajectory. Each one of those state vectors would contain the position and velocity state, so three-dimensional position state, three-dimensional velocity state. Combining all of those state vectors together gets us this very high-dimensional feature vector. We can then take that very high-dimensional feature vector and map it down onto a lower-dimensional feature space using a technique known as principal component analysis. So we can see that lower-dimensional feature space. In this case, it's a two-dimensional space on the left-hand side. So each one of the points in that space maps to one of the trajectories on the right-hand side. From here, what we can do is just group together points in this feature space that are close together. These points represent trajectories that have similar properties, and by performing a clustering algorithm, we end up with a set of clusters, each of which contains a group of trajectories that are similar to one another from an astrodynamic perspective. From here, we can take from each one of these clusters only the single element that is most similar to all of the other elements within that cluster. In this way, we're reducing our space of how many trajectories we need to use for this analysis. So we're drastically reducing the number of computations, but we're doing this in a way that still preserves sort of the fundamental motions that are possible in this cislunar regime. So what we're left with is a set of trajectories that is still representative of all of these different possible motions, but it's a much smaller trajectory set. So we'll repeat this process with the L2 manifold trajectories again. We're going to map each one of those to a point in this astrodynamic feature space. From there, we're going to group together the points that have similar properties into a set of clusters. And from there, we'll select only the single point from each one of those clusters that is most similar to the other elements. Now what we can do is search for low-cost trajectory sequences. So this step is going to consist firstly of building what's called a motion primitive graph corresponding to the remaining trajectory. So we take each one of those points that we had left over after that downsampling step in the previous step. We'll take each one of those and map those to a node on this graph. We'll also stick onto that graph the departing orbit node and the destination orbit node, and then we'll connect the nodes in this graph with edges. And the weights of those edges are going to represent the state differences between those corresponding trajectories. So what we mean by that is if we take two nodes on this graph, and these are representing two trajectories on the right-hand side, when we connect those with an edge, if those two trajectories have large state differences between them, meaning it would take a large delta V to get from one of those trajectories to the other, then we will end up with a larger edge weight. And in this way, these larger edge weights will discourage pathfinding algorithms that go from the departing orbit node to the destination orbit node, will discourage those algorithms from using that weight in the path that they find. So from here, we can just search this graph for low-cost paths. So every path that we find through this graph that leaves from the departing orbit node and finishes at the destination orbit node will represent a different sequence of trajectory arcs that we could take to get us from that departing orbit to the destination orbit. Right? So every path that we find is going to be a distinct sequence of trajectories. And we can end up finding what we're looking for here is the lowest cost path, right? So the path that has the lowest total edge weights from start to finish, which is representing a trajectory sequence that would take a relatively small amount of delta V to get from that departing orbit to that destination orbit. This graph search process is done in one of two methods. The first is a simple depth first search to find all of the different paths through the graph. From there, we can take all of these paths and just sort them by edge weight to find the best or the lowest cost paths. The second way we can do this is what's known as Yen's k-shortest path algorithm. It's a bit of a more sophisticated algorithm. It implements Dijkstra's algorithm to do this graph searching, and in that way, it takes into account the edge weights as it's doing the searching process. So that's a more efficient search algorithm. From here, we can refine these trajectory sequences into continuous trajectories. So we can, once we've found a path through the graph that takes us from the destination orbit or from the departing orbit to the destination orbit, we can take that sequence of trajectories and refine that discontinuous sequence into a continuous trajectory. This has previously been demonstrated with high thrust applications, but in this analysis, we'll demonstrate how you can do this as well via a low thrust optimal control problem. We're going to see more of that later on, so we'll dive into that in just a little bit. From here, we're going to cluster together solutions that have similar properties. So one of the issues that we find with this algorithm is that once we've searched through this graph, we found a large set of different paths that take us from that departing orbit to the destination orbit. What we may end up finding is that many of the paths that are returned by this algorithm may be very similar from a qualitative perspective. So what that means is if we were to look at, for example, these three paths on the screen that the algorithm spits out, a decision maker looking at these might think that these are all very, very similar from a qualitative perspective. There's not really all that much value in presenting these as three unique trajectory options to a decision maker, right? So from their perspective, these may look so similar that there's not really a clear reason to present all of these, right, separately. And so for that reason, what we want to do is group together the paths that are very similar from a qualitative perspective to just be sort of a single solution. So if our algorithm returns 100 different paths, and of those 90 of them look nearly identical, and then another 10 of them look nearly identical as well, then what we would rather do is instead of returning 90 unique solutions and 10 unique solutions, we'd rather group those together to just be just two paths that are distinct and that we could present to decision makers. So the solution here is to cluster these return paths, these sequences of trajectory arcs, one more time. So how do we do that? Well, we could use a feature vector that encodes the astrodynamic properties of these trajectory sequences, just as we did before, right? So we could map each one of those sequences to a high dimensional feature vector, project it down into lower dimensional feature space, and then use a clustering algorithm to group together trajectories that have similar properties. The issue with that is that visually similar trajectories don't always end up being similar in this astrodynamic feature space. So what do I mean by that? Well, if we were to take these three visually very similar trajectories and just as I said, find an astrodynamic feature vector representing the properties of these trajectories, map it down to this lower dimensional feature space, what we may end up finding is that these visually similar trajectories may not end up very close together in this feature space. And so they may not end up being grouped into the same cluster. What we end up with here is an unintuitive grouping of clusters, where two trajectories that are visually quite similar may not end up in the same cluster. And similarly, we may end up with two trajectories that are in the same cluster, but they look visually quite different. So what's a potential solution to this? Well, one way we could approach fixing this problem is to borrow the concept of a convolutional neural network from machine learning. So a CNN is a type of machine learning model that can be used for image processing tasks like image classification. So in the example we have on the slide here, we can see how this network has learned how to take an image of a hand-drawn digit, so a 1, a 2, a 3, take an image of that digit and process the features of that image and learn to put a label on that image, right? So put a word label attached to the input image. So one particular type of convolutional neural network is known as VGG16. So this is a very high performing and open source CNN that was trained on 14 million images as a 1000 class image classifier. So what it does is it can take in these input images. In this case, we have an image of a boat. Those images come into the network. The network processes the images, finds features of those images, and then maps those features to an output class. In this case, it's boat. So the earlier layers of this network do what's known as encoding this 2D image as a one-dimensional feature vector. So they're taking that taking that two-dimensional image rather, and they're encoding it down to one very long feature vector that encodes some of the semantic properties of that image. The later layers of this network then take this high-dimensional feature vector and map that vector to an output class or label. So one technique that we can do here is detach these most abstract specialized layers from this pre-trained VGG16 network. And what we will be left with is what we could consider a generic image feature extractor. So what do I mean by that? Well, we can take these higher level layers that were trained to take that high dimensional feature vector and map it to a specific class label. We can just remove those layers and just keep those earlier layers, those layers that were just there to learn to extract the features from this image that represent that image's semantic content. What we're left with is this network that we can pass images into to end up with a high dimensional feature vector, a vector that once again we can project down to a lower dimensional feature space using a dimensionality reduction technique like principal component analysis. So in this case, we input that image of the hand-drawn number 8, and this network can map that to a two-dimensional vector in this case, as we see on the right-hand side, that represents that input image. So this is a concept known as transfer learning. And what we can do here is take this transfer learned pre-trained VGG16 network and pass into it a set of images. And what we will tend to find is that images that have similar semantic content will tend to be placed very close together in this feature space. And so that means that when we input these images of 8s and these images of 5s, we will tend to find that the 8s end up grouped together and that the 5s end up grouped together in this feature space. What's interesting about this is that even though this network was trained on images that are completely different from trajectories, we can still pass in images of these trajectories into this network, and we can still use it to map those images to points in this feature space. What we will tend to find when we do this is that visually similar trajectories tend to be mapped to close together points in this feature space, despite the fact that, once again, this network was not trained on images of trajectories at all. So the number of clusters in this clustering process was determined automatically via a concept known as cluster assignment scoring. So what this means is we assign a better score to a clustering assignment if the elements in clusters are more similar to other elements within that same cluster and more dissimilar from other elements in different clusters. So what we can do is try a large number of different amounts of clusters. We can tell it, try to do 2 clusters, try to do 3 clusters, try to do 4 clusters. And for each of these cases, we can give the clustering assignment a numerical score. And then from there, we can just pick the assignment that had the best score to automatically determine how many clusters was appropriate for this particular case. When we did this process, we tended to find that visual-based feature vectors, that is using this convolutional neural network process, using those vectors tended to score about 33% higher than using astrodynamic-based feature vectors alone. And using hybrid vectors, that is concatenating these astrodynamic and visual-based feature vectors together, using that form of clustering tended to score about 39% higher. So what we can take from this is that the introduction of these visual-based feature vectors extracted from this transfer-learned convolutional neural network tended to improve clustering results. That is, it tended to result in clusters that were more similar, that had elements that were more similar to other elements within that same cluster. So this is what these clustering results tended to look like. So in this particular example, again, we're looking at a transfer from an L1 Lyapunov orbit to an L2 Lyapunov orbit. And what we see here is the clustering results for all of the different trajectories that the algorithm found. So this is how the clustering algorithm attempted to group these results together. What we see here is not a very good clustering result, right? So we see that using these astrodynamic-based feature vectors, the clustering procedure found only 2 clusters. And we see that these clusters are not very cohesive, right? So we see the elements in the left cluster. There are very, very different trajectories presented within that cluster, trajectories that we would not intuitively put together in the same cluster. And so for that reason, these clustering results are not very good. We would like to further refine these clusters, and we really only want to group together trajectories that are visually very similar. And we see here that this clustering procedure ended up grouping together trajectories that are visually quite dissimilar. So that's a disadvantage of using this astrodynamic-based sequence clustering. Attempting to use visual-based sequence clustering yields slightly improved clustering results. So in this case, the algorithm found 5 clusters rather than just 2. We see in this case the clusters are slightly improved compared to the previous case, particularly if we look at that cluster in the top right. We see that there is trajectories in that cluster that are visually quite similar to one another. And that's a good thing. That's what we're hoping that this clustering procedure is going to do. However, there are still some trajectories, particularly in the bottom 2 clusters that we see that probably should have been grouped together with trajectories in that top right cluster. And we also see in that very leftmost cluster, once again, we see trajectories that are very visually dissimilar to one another that end up grouped together. That's not a good thing. So, using these visual-based feature vectors did yield an improvement in the clustering results, but there's still a long way to go here. There are techniques that exist to further refine clusters, which would be a good thing to apply here. We could take some of these larger clusters and break them up into a larger number of clusters that have smaller numbers of elements within them. So that would be a useful technique here. And again, this is utilizing a convolutional neural network that was trained on an entirely separate data set. So we could improve these results, likely improve these results by training that network further on some images of trajectories rather than just what it was initially trained on, right? So there are ways that we can improve these results. That said, this is a promising start, and it's a way to improve the clustering results of astrodynamic-based feature vectors alone. And it does suggest that using these visual-based clusters is a good direction to move in. So now we're going to talk about the results here, and I'm actually going to shift this over to Dr. Brian McCarthy, and he's going to talk us through what we're looking at here.
All right, thanks, Fabio. So what we're seeing on the screen here is some results from the algorithm that Fabio just talked about. And I'll mention that this this problem, looking at going from an L1 Lyapunov orbit to an L2 Lyapunov orbit is kind of a classic problem in multi-body dynamics. And it can be, solving this problem can be achieved through more traditional methods, Poincare maps, things like that, to find connections between these two types of orbits using manifolds. And so what we see here is that many of these trajectories, or pretty much all these trajectories, are all discontinuous. And the idea here is to try to get that discontinuity down initially through the initial guess process, and then pass this to another algorithm that can sort of stitch the trajectory all together. And so the next sort of step in this process is taking these initial guesses and seeing how they behave when we transition them to be fully continuous. And so the way we do this is using low thrust paired with collocation to stitch these different trajectories together. So if we pick one of these initial guesses, which is shown on the left-hand side here, we're going from the L1 orbit on the left to which is in orange, and then we're going to the pink L2 orbit on the right. We can see that there's a slight discontinuity in the trajectory, but it sort of follows a shape or a direction that we would ideally want. And so if we pass that to a collocation algorithm using a low thrust engine, it does connect the trajectory together, and it maintains the same basic characteristics that we see in the initial guess process. So ideally, that's what we want. Is we want to find an initial guess. It's going to have some characteristics that we prefer, and that those characteristics are maintained when we move it to being fully continuous. So on the right-hand side here, we can see that there's small white vectors that indicate the direction of thrust, and so there's a little bit of thrusting that's required to connect this trajectory together. So if we go to the next slide. So again, we looked at a planar problem in the circular restricted example we used in the previous slide. However, solving these problems in the spatial problem is a lot more difficult, because you now go from 4 dimensions to 6. And so using more traditional methods becomes a lot more difficult, because you can't look at all the dimensions all at once. We can kind of look at 2 dimensions and maybe 3 or 4 if we kind of do some fancy things with what we're looking at. But if you want to look at all 6, it's really, really challenging. So using an algorithm like this helps look at all those dimensions using a computer, essentially. So on the left-hand side, we have an initial guess that goes from a L1 northern halo orbit to an L2 southern halo orbit, and we can see that there's a decent discontinuity between the green trajectory or the green segment and the orange trajectory, and that's the arc coming off of the L1 orbit. And so if we pass this to a low thrust collocation algorithm, we can see that the white thrusting vectors are included in there as well, and that while the geometry isn't exactly the same, it is sort of roughly maintained between the two. And so this kind of shows that this process, while they're not perfectly continuous, or the initial guess algorithm doesn't necessarily need to give you a perfectly continuous initial guess, it can be enough to sort of get when you have to solve the problem, to get it fully continuous at the end, that it's kind of puts it in the basin of convergence successfully, to give you a solution that you'd ideally want to carry the basic characteristics in the end. So if we go to the next slide. So this is the last example here, going from an L2 southern halo orbit to a DRO. And so the challenging part about solving this particular transfer problem is that L2 southern halo orbit has a significant out-of-plane component in the Earth-Moon rotating frame. And a distant retrograde orbit, DRO, is purely in plane in the Earth-Moon plane. So accomplishing that plane change is challenging to do in a propellant-efficient manner. And so on the left-hand side here, we pass this through our algorithm to find some initial guesses, and we pull this one out, and we can see that we have an arc that leaves in orange from the halo orbit, goes sort of way out through the system, and then we have a green arc that arrives on our distant retrograde orbit. And I believe we use a series of different different types of orbits in here that the algorithm could look through to find a feasible path. So I know Fabio talked a little bit at the beginning about L1 Lyapunov to L2 Lyapunov halo orbit, where we needed manifolds to transit between these two orbits, but that doesn't necessarily have to be the case always. We can use different types of arcs in between in order to construct these paths and sort of different segments of these paths. And so that's what's going on here. We have the initial guess on the left-hand side, and then if we pass this to, again, our low thrust collocation algorithm, it makes the trajectory continuous by using some thrusting arcs in between to sort of maintain the geometry characteristics of the trajectory, which is great because we can see that it's pretty well maintained between the initial guess we get on the left and the final solution that we get on the right. I go to the next slide.
Awesome. Thanks, Fabio. Brian. Yeah. So what conclusions can we draw from this? So firstly, Cislunar trajectory design is very challenging, right? So even for a PhD level expert, finding these transfers in cislunar space can be very time intensive. So this automated path planning tool that we've developed quickly computes a variety of these transfer options and attempts to automatically sort them into logical groups. As we've mentioned, this sorting process is very challenging. It's a very chaotic and difficult problem to solve, but we've made some great first strides in performing that automatic grouping. So operators could use this tool to provide several distinct transfer options to decision makers and do so very quickly and with minimal user input. We've also learned here that machine learning is really not the right tool to solve this entire problem at a very high level. The cislunar environment is just too sensitive. So what do we mean by that? Well, we saw how a convolutional neural network could be used to enhance this problem. One way you could approach this is to just use a generative convolutional neural network to input, for example, an image of the starting trajectory and the destination trajectory, and then you could just tell this generative network to generate an image of what would the trajectory look like to get us from that starting trajectory to the destination trajectory. But that would not be a great way of solving this problem because the cislunar environment is extremely chaotic and extremely sensitive, as we've been mentioning throughout. And so what we would find is that approach to the problem that attempts to solve it purely from a machine learning standpoint would likely yield terrible results. However, applying machine learning in very specific ways to this problem, for example, the clustering procedures that we talked about, that's all machine learning. This dimensionality reduction technique, that's machine learning as well. Applying ML in that way can be extremely useful. So picking and choosing the applications to machine learning to enhance these challenging aerospace problems, that really is the correct approach. So also, as missions continue to strive for increased autonomy, using a tool like this automatic path planning tool can help avoid spending a significant period of time planning and replanning trajectories, right? So if something changes, if a mission needs to adapt to to a changing scenario, we want to be able to replan these trajectories very, very quickly, even in this chaotic cislunar space. And so improving the responsiveness of space operations is important from this security perspective, right? What if something changes and we need to replan our trajectories? We don't want to have to take an entire team of several people and have them spend, several days or however long it might take to replan these trajectories because they are so challenging. We want to be able to replan them automatically and very, very quickly. So other applications and extensions of this tool would be scenarios like, what do we do if we have an object that's in a known orbit and we lose track of it, right? Where else could it have gone from where it was in a given amount of time? Right? So that's a way that we could take this tool and sort of approach it from a different direction with some modifications. We could attempt to search for what known paths could this object take. And where could it end up after a certain amount of time, right? So that's a sort of a different approach to the problem, but it's one that uses a lot of the same fundamental building blocks, and it's an extension of the tool that could be reasonably made. Another one would be, what do we do if we have an observation, but we don't know what object it belongs to, right? So which of some catalog of known objects is that observation likely to belong to, given the past observation histories of those objects and the known trajectory paths that are within this cislunar regime. So again, approaching it from a different angle. Well, we have this catalog of a bunch of different known trajectory paths within the cislunar regime. We know the ways that objects are likely to move within this regime. So, if we have an observation that we have not mapped to a known object, which of the known objects could this observation be from, right? So it's another, similar extension of this tool. And so again, we see that there's many different ways that we could adapt this tool. and use it to solve some of these very challenging problems that right now there are not great solutions to. And so, we see that there's this need for this increased autonomy and this increased ability to plan paths in this regime very quickly, and that sort of is what motivated the development of this tool in the first place, right? All right, so that's all we've got for you guys. So thank you all very much. I really appreciate you guys listening, and yeah, we can open it up to questions.
Yeah, thank you very much. That was very insightful. We do have a few questions to start, and for everyone, be sure to add any questions to the Q&A as you think of them. And the first question we have, could you define what the cost function is? Talking about propellant load, kinetic energy, transfer time from L1 orbit to L2 orbit, or something else?
Yeah, that's a great question. So we've heard this a similar variant of this question many times. One aspect that this algorithm does not consider is transfer time. So when we're putting together that motion primitive graph, and we are assigning weights to those edges, that's effectively the cost function of this analysis, right? So how do we assign those edge weights? Those edge weights are based on what is the smallest state difference between those two trajectories at any point along those two trajectories, right? So it looks at several discretized points along both of the trajectories, finds which 2 points are closest together in position and velocity space. There's some weighting that's applied there in terms of position and velocity, so we can weight them equally, or we can say, well, we care more about the trajectories being physically close together, so we want their positions to be close together, but we don't care as much about velocity. So in that way, we can apply a weighting parameter there to weight those two differently. But that's effectively what it's doing, is it's finding the difference between the states of those two trajectories, and that is effectively the cost function, right? So a higher cost means a higher state difference between the two trajectories, which would correspond to a higher fuel cost that would be necessary to get from one to the other. So a way that we could enhance that is to additionally consider the time that it would take to use those trajectories. Right, so that is an aspect that has not been considered in this analysis, but it's certainly one that would be worth exploring, because right now, two trajectories that are identical in fuel cost but extremely different in terms of time are going to be weighted equally.
Right. Another question is, what makes the astrodynamic feature vector applicable for the initial clustering step, but not for reclustering the full path?
Yeah, that's a great question. It's from a theoretical perspective, I think it's quite difficult to tell. These feature vectors are very high dimensional, and they're just sort of our best attempt at ordering finding order in this extremely chaotic and difficult to order system. So from a theoretical perspective, I'm not sure there's a great reason why it is applicable in that initial clustering step and then not in that sequence level clustering step. From a practical standpoint, it just seems to work that way. When we do the clustering procedure on these sets of trajectories, not the trajectory sequences, but the individual trajectory segments, when we use astrodynamic-based feature vectors there, it tends to produce pretty good clustering results, good enough that the algorithm has been able to consistently find the paths that we needed to find. However, when we've attempted to apply that astrodynamic-based sequence clustering at the sequence level, right? So after we found the paths, trying to do that astrodynamic approach there, that has tended to yield worse results. And why exactly, I'm not 100% sure, but in practice, it just has appeared not to work. And so, attempting to improve those results, we stumbled upon this visual-based feature vector approach. It's possible that approach would even be useful in the earlier step as well. We haven't attempted to apply it there, but could be worth exploring. That's a great question. Hopefully that answers it.
Another question is, you mentioned that the algorithm can be used several different departing or destination trajectories, allowing for mission design flexibility. What's the limit on departing/destination trajectories that the algorithm can consider?
That's a good question. There is not any sort of hard limit. What will happen is the more trajectories that you consider in this analysis, the computation time starts to blow up. sort of the way it handles using a large number of potential departing and destination trajectories is you imagine that motion primitive graph that we talked about. What it effectively does is it adds each one of those as a node to that graph, and then it adds a sort of a dummy start node that is connected to each one of those nodes. So it's essentially increasing the complexity of this graph, which is going to drastically increase the computation time depending on how many nodes we include in that graph, right? So that is one of the things we've had to balance here, is the computation time of the algorithm. We want that to remain relatively fast because, again, we want this to be a very quick algorithm to run. However, the more trajectories that you consider, the larger your solution space. Theoretically, the better your results are going to be, but also the longer it's going to take to compute them. So that's sort of just a practical limitation. Of course, in the ideal world, you're running this on, in parallel with, with cloud resources or something like that to improve the computation time. And so in that world, there's theoretically not a limit to how many potential starting and destination orbits you can consider.
Another question we have is, does the program enable the addition of constraints, i.e. avoiding a certain region or family of orbits? Additionally, can you alter the optimization parameter, delta V versus time, for instance?
That's a great question. So in terms of that last part, that kind of ties back into that first question. As of right now, there isn't a time component to the weighting of the edges in this graph search process. However, I do think that is worth adding. We just haven't done that yet, but that's a great direction to move this analysis. In that case, I do think a weighting component would be the way to go. So you can tell it I want to prioritize time or I want to prioritize delta V, and there's some sort of scaling parameter there that you can use. I do think that would be the right approach. The first part of the question, I'm sorry, could you remind me of that?
Yeah. Does the program enable the addition of constraints, i.e. avoiding a certain region of family of orbits?
Gotcha. Yes, that's a great question too. Right now, no. However, the first sort of step in this process is building this kind of high-level itinerary graph, where you tell it, I want to go from this starting orbit, and then I know I want to go from there to one of these orbits, and then I know I want to go from there to one of these trajectories, right? So you're kind of telling it what trajectories to even consider in the solution space at all. And so in that way, you can exclude any regimes that you don't want to go to, right? You just don't put them in that high-level itinerary graph. The idea as well, if this was, kind of like an application that any user could use, we might have some sort of pre-made high-level itinerary graphs where we tell it this graph, this graph uses this particular area of the solution space, and then this other graph uses sort of a different solution space. And those might be some pre-made graphs that users that don't have the experience to sort of generate those graphs might be able to use, and then other more experienced users can be more fine-tuned with what trajectories they're allowed to use in this analysis. However, there's not really any built-in framework right now to explicitly, if you don't have that trajectory design expertise to build those itinerary graphs, there isn't any way to intelligently and automatically build those graphs for you, at least not right now. That might be a good direction to move as well, but right now that's sort of something that's left to the user, right, to build these itinerary graphs. And like I said, we can have a few common design scenarios that we already have graphs built for, but for other more specific scenarios, there would have to be a trajectory designer there to build those high-level itinerary graphs.
Yep. And one more question. How difficult would it be to custom train the convolutional neural network on trajectory images to improve the visual clustering results?
That's a great question as well. I'm not sure. It's a great question. The issue with training the network further is we need to have something to train it against. So the network was initially trained this very large set of 14 million images that were painstakingly labeled. So human beings looked at 14 million images. Wasn't one guy, probably. It was probably several people that looked at 14 million images, and they labeled each one of them. This one is a boat, this one is an airplane, etc. And the network has then learned to map those images to those classes. The issue when you introduce trajectory images is there is no labeling, right? How do we label, each of these trajectories? There isn't really a great way to do that. And what would the labels even be? Would it be a label saying this is a, manifold trajectory of a Lyapunov L1 orbit, or would the label, how fine-grained will these labels be? It's a challenging problem, and even if we figure out how we want to do that, we still have to have somebody manually sit down and label a bunch of trajectories. That's very challenging to do. However, one thing we can do is utilize a set of images that is more similar to the target images. So the images that this convolutional neural network was trained on are completely dissimilar from these images of trajectories. They're images of boats and planes and trains and cars and animals and things like that. They're really visually not similar to trajectories at all. Typically, when you do a transfer learning process like this, you want to have the two data sets be as similar as you can have them be. So for example, if I trained a network to distinguish between types of cars, I'd probably have an easy time using transfer learning to then have that network distinguish between types of trains, right? Because they are data sets that are visually very similar, right? A train and a car visually are quite similar versus right here in this case, we're training on animals and vehicles, and then we're mapping them to trajectories. They're visually quite dissimilar. So if we were to use a data set that was perhaps more like lines and squiggles, for example, the labeling letters and numbers, maybe we might see improved results there. We haven't attempted that, but training the network on a more similar data set like that, that might be the way to go. How challenging? I think it's challenging. It's doable, but it's not a very simple problem. It's using transfer learning for a network for two data sets that are so dissimilar, particularly when we have one that is very difficult or almost impossible to actually label. It's very challenging. So hopefully that answers your question.
Yep. And then our final question, this one's toward Danny. Would these features be included in the base license of FreeFlyer, or would this be an add-on or separate tool altogether?
Hey, thanks Regis, and thanks Jeffrey for the question. Right now, this is an in-development feature of our Deep Space Trajectory Explorer model, and parts of the algorithm is used in DST in the integration for transferring from low fidelity to high fidelity. And you can also look at aisolutions.com/DST for more information on that. And I'll put that in your comment as well.
Well, thank you, Fabio and Danny, for answering all the questions. So we just have a couple before you go slides for everyone. If you want to hit next. Yep. So our next quarterly webinar will be Flight Dynamic as a Service. This will be Wednesday, September 25th, 1 to 2 p.m. Eastern. And our speaker will be our very own Scott Lowe. And you can simply scan the QR code on the screen to register now to reserve your seat.